Okay, welcome to the lecture today. We've not seen us since 2 weeks now, right? So we have to talk a little bit what happened 2 weeks ago, because probably you already forgot. Then I'm working on your homework, and I'm nearly done, but I still have to correct 5 of them, so you will get them till end of the week. Okay, so before we will start the new homework, you will get the feedback of your homework. This one, and then you told me you don't have a partner for the seminar, right? Because I saw you on the list. Who else has not a partner for the seminar? Okay, then you have partners now, okay? So you two can do the seminar together. You still have 2 appointments. You have the dates for the appointments? Yes? Yeah? Okay, very well. Today we will also listen to a few of them, but those, I didn't got all the summaries. So those who will present today and didn't send me the summary, please send me the summary in the break, okay? Other question, homework, groups are done. Then I think we can start with, what did we do 2 weeks ago? So last week was vacation, and what happens 2 weeks ago? Yes, so? Why they happen. So we talked about light scattering, why they happens, different phenomena. What do you remember? What light scattering, why it's important, how does it work? Yeah. So how the particle, how the intensity changed, why the sky is blue, why the sunlight is, sunrise is red. Why is the sky blue? Yeah? Why? Me scattering. Are you sure? Because of scattering in general. It's because of scattering. So basically we talked about how can light interact with matter? In 4 ways. In 4 ways. Reflection. Reflection. Scattering. Scattering. Refraction. Refraction. And transmission. Transmission. That's it? Yeah? Absorption, right? 5. Okay. So why is the sky blue now? So scattering, one of them, right? So the scattering is important. The light gets scattered by the molecules, by the aerosol particles, by the droplets. And what kind of scattering? Or is there just one? Is there just scattering? What do you think? Yeah.
I remember about the Rayleigh equation.
What again? Which one do you remember? Rayleigh. What is Rayleigh?
It's the scattering of
Yeah.
the small particle.
Yeah, it's the scattering of the small particle. And what's the difference from me scattering to Rayleigh scattering?
Me for the bigger particles.
Yeah. So me is for the bigger particles. So where do we see the effect of me scattering? Yeah?
When we talk about dust.
Not necessarily, not dust. Dust can be Rayleigh scattering.
Or water droplets.
Water droplets. Why water droplets?
Because there is also a bit transmission.
Yeah, there's a bit transmission, but why we're talking about scattering now, right? There's me scattering and Rayleigh scattering. But why for the droplets, the water droplets, we have me scattering? Why not Rayleigh? Can I dice, or why me scattering? Yeah? And the lambda 400 is the wavelength, right? And the wavelength depends on the color, so between 400 and 700. And there is a dependency to the wavelength, and this is why we get. That's correct. So the intensity of the scattered light is wavelength dependence. It's 1 divided by lambda to the power 6, or to the power 4, or to the power 8. 6, right? 1 divided to the power lambda to the power 6. So blue has a shorter wavelength, and since it's 1 divided by lambda, it's scattered more intense. The intensity is higher. This is Rayleigh scattering. But why do we say for the sky Rayleigh, and why for the droplets Mie scattering? Yeah?
The directions.
Yeah, both are different. So direction is for both important. But again, why Mie scattering for clouds? Yeah? Exactly. So what is the important point? Scattering is effect. And scattering is different from what? You already said it, from? The size of the particle. The size of the particle has an extreme important influence how the pattern looks like and how the intensity is. And for very small particles or molecules, we can use the Rayleigh theory to describe the scattering, the pattern, the dependency on wavelength, the dependency on particle size. But when the particle itself grows in size, the Rayleigh equation does not correctly describe the scattering. So which one do we take? Mie. And then the angle direction changes, the dependency from the size changes, and so on. And this is why we get white for the water droplets and blue for the sky. Since what is in the atmosphere? What is there? Yeah, small molecules and small particles. And what is in the clouds? Water droplets, exactly. In the clouds is water droplets. And water droplets are larger, exactly. And this is why they are white. And when we have a thunderstorm, what is the color? Gray. And why it's gray? Yeah? It what?
Like it decreases the intensity of light passing through it.
Yeah, but why? That's correct, but why?
Because
Yeah.
it is more intense.
Yeah, no. If it's more intense, it would be white. If it's more intense, it would be white.
It would block the light.
Yeah, but why?
Concentration of water droplets. Molecules is more blocked.
Exactly. The concentration of droplets is higher, and what happens if the concentration is higher?
It absorbs more light.
No. The volcano is black because it absorbs light. We have scattering, right? Scattering is different than absorption. But what happens in the thundercloud?
It does not let it pass.
It does not let it pass because of
More scattering.
more scattering. And what happens if the light is scattered all the time? It cannot escape. It's like a labyrinth, okay? So really try to distinguish between scattering, absorption, refraction, transmission, and all these things, and different models to describe scattering, absorption, and so on. And Mie and Rayleigh are different models to describe the scattering of light based on molecules, aerosol particles, and so on. And when you take the model, depends on the size of the particle. It's always the same answer. Depends on the size of the particles. Good. Then we also discussed, there was one thing really wondering because the sky is blue and then it's red. What shouldn't happen, basically what should happen in between? What should we observe normally? Yeah, so we should go through the color through the rainbow, right? We should see green and yellow. And there was only one person who sees green, and this is you. Yeah. But we don't see green. And this is, does anybody remember why we don't see green? Because normally we should have blue, and then comes green and yellow and red, right? Or blue, red, green. No, it should be green, blue, green. Yeah? Yeah, we have Chapuis absorption. And this is when the O3 breaks down in interaction with the light. Good. This was repetition from last time. So I will ask you these questions in the exams. You should be able to answer them. Okay, so please be aware of this. And for today, I switched a little bit topics due to the second homework and due to the free day. And this means that today we will talk about one of my favorite topics, which is weird because always when somebody asks me what I teach in the next lecture, I say, oh, it's one of my favorite topics, since I like nearly all of these topics. But this is one of my favorite topics because it's my research topic. And this is where I try to build up a research group at the moment. So we will talk about adhesion. And if you look in the curriculum, or the schedule, not curriculum, we see, okay, there was the free day, which I was not really aware of. And normally we had 2 coagulation lectures and then the homework. And now I switched that I want to have adhesion and 1 coagulation lecture because I want to have adhesion as part of your homework. And coagulation, and then we make the experimental methods. This is something I could do today, but I want to prepare something for it, and I need more time. And then we talk about carbon nanoparticles, or there's still a typo, and finally about nanorobots. One thing is, when we talk about the oral exam, just that you know, in the oral exam, I will ask you questions more or less in the same way I ask these questions each lecture. So basically, I will ask you exactly the things I ask you when we talk about what do you remember. Yeah?
About the oral exam, do you know already which day the oral exam is?
Okay, yeah, it's basically the day. You should have a day for an exam or something.
Not yet released.
Okay, it's not released. I have, because we have to figure out about the schedule and when your exams are, okay? So I will prepare this for next week, and then we can talk about the appointments, yeah?
But you know that it is in July or
in July? Yeah, in July. And one part, which is also of the oral exam, is, so it's half an hour, and I will ask you these questions, and I will very often, this is also for today, ask you, I want to see if you understand the model. So exactly like today, I want to figure out that you understand there are 5 ways how light interacts with matter. And I want to see that you know that ray light and me is scattering. And these are different equations to describe the scattering dependent from the particle size. And if you come with, yeah, the light sky is blue because there's absorption and there's scattering, then I see that you don't understand this. Okay. So if you just make name dropping. So if you don't know anything, just say, I'm not sure, I don't know. But I want to figure out if you're able to relate the equation to the part the equation describes. And I want to figure out if you really know that scattering is something else than absorption. And that the equation describes scattering and not absorption and scattering and somehow something with light. Okay? This is how I will test you in the oral exam. And what I also will probably do is I will take your homework and take a look at the stuff you wrote in your homework. Okay, so also be aware. The nice thing is you can do homeworks with other people, but you should know what you wrote in your homework because this is what you sent to me. Okay, so if you look for papers in homeworks, you should know them. I don't need the title, I don't need, not that, but you should know what you put in your homework, and I will ask you for these things. And this is for me quite good to test the knowledge. Any questions to this? Good. Then, what will we do today? And today we will talk about adhesion, and we will figure out why adhesion is so important and how it works. And then I will see, already in the beginning, we will take a look if there is an application of adhesion. And one thing, and I wrote it down before, is because it's really important for me, and students very often have problems, I want to develop a model how adhesion, basically what is adhesion? It's something we did all the time in transport. Adhesion is a force, very good. Adhesion is a force. So how adhesion force, so basically it's something we should put in the balance between two particles in air works. That's the task for today. Develop a model how adhesion force between two particles in air works. So we just look at two particles, not more. What kind of particles? Probably? Yeah? Spherical, the most simple. Spherical makes the equation simple. So we look at two spherical particles. And there's adhesion. And the same with scattering, which is part of interaction with light. And then there is ray light and me scattering. I would like to do the same with you with adhesion. Because I also often see that the students mix the things up. Do you know any adhesion forces? Just my... You know some.
Yeah, but I don't remember
At least one.
I don't remember the English names right now.
One is easy to remember because it's named after, it's a name. It's a Dutch name. What kind of adhesion force do you know? Van der Waals, exactly. So you know Van der Waals forces, and there are more forces. And adhesion is the umbrella term and consists of multiple forces. And this is what I want to get you, and we will start quite simple, because we will start with adhesion forces between ions. Could be also atoms, whatever. And then we go from ion to molecule. And then from particle to particle. So we will start ion-ion, ion molecule, 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 particle, particle. And for all these things, we will take a look at the red arrow. And from mechanics, you know, a red arrow is always a... Red arrow always is a... You already said the word? Force, exactly. So it's adhesion force. And I want you to understand we go this, I hope at the end you understand why. And after this, we will probably already have one part for the picture, and then we will try to make this picture more compact. We have one limitation in the lecture due to time and due to deepness of the topic. We look at particles in just a specific case. Which one? It's already on the board. Yeah? No, not one dimension. That's not the point here.
Particle, particle.
Yeah, but for which case? I mean, this one at the end refers to this one. But for which case? Yeah? In air, exactly. So this means the model I show you only works in air. And this means if we go into liquids, then the model changed a little bit. There's theory about it. So the last 10 years I tried to figure out how this works in air. The next 10 years I try to figure out how it will work in liquid. Okay? So it's quite easy how it probably works, but also when you mention the force, be aware where the model, what are the assumptions of the model? The assumption of this model we will develop is it's in air. And we will see why this assumption is important. Good. I would like to start with some examples why adhesion is important. And there are technical applications related to adhesion. Who knows Andreas Geim? All of you should know him. Who has never heard about Andreas Geim? You have heard about him? Okay. Make a guess, who is Andreas Geim? A scientist, very good. And if you look at this slide, you see he is a Russian, German, Dutch, English scientist. And he considers himself a European, which I really like. And this is one of his papers from 2004, Electric Field Effect in Atomically Thin Carbon Films. So do you have an idea who is Andreas Geim? Or what is this paper about? What could this be? What do you think?
Like who the guy is.
Not who the guy, but what is the paper about, basically? Just 1, 2 words. Yeah? It's not about optical fiber. It's something much, much more, not more general, but different in topic, and something all of you know, for sure. Any idea? It could be used for displays, yeah. Basically, when he talked about it during his Nobel Prize talk, he said that he didn't patent it because he said it can be used for displays, but he didn't give more technical details about it, and this is why he didn't patent it. I don't know if the story is true, but
It's about nanochips.
yeah, you can call them nanochips. That's but a very specific one, a very famous one. It's a material, very famous material. Yeah? Graphene, very good. It's about graphene. So Andreas Geim developed, synthesized, produced, I don't know how you will call it, the first time graphene. What is graphene? Graphene is a two-dimensional structure. It's a crystalline carbon material, but two-dimensional. So it means that it's the thinnest material we have, one of the strongest we have. And it's a nanomaterial, of course, because it's atomically thin in one dimension. And he basically made it for the first time. It was quite an interesting thing, because based from the calculation before, it was not clear if this material will exist. Because the calculation showed that the material should have a wave structure due to how the atoms arrange, so it will not be flat. And he proved the material is flat. And the way he did it was quite cool, because he took a highly orientated graphite, pyrolytic graphite. So it's graphite, you can buy it, it's quite cheap, 1 millimeter thickness. And then he sticked it to something. And then he took a Scotch tape and just ripped off layers of layers of layers. So you can win a Nobel Prize with a Scotch tape at the end. Because if you take up more and more layers, at the end, one of these monolayer will left over. Then you just have to bring it free from the Scotch tape or from the material where it's on. And then he investigated and proved this is graphene. So on his work, for his groundbreaking research on graphene in 2004, he got 2010 the Nobel Prize. So he got it with another guy. The guy, when I'm have the story correct, please correct me if it's not the case, but the right one is his pupil. He was a student of him, and they did it then together, as far as I know the story. So then they won together the Nobel Prize for graphene, which is nice, Nobel Prize for nanotechnology. Is also one of the reasons why we expect a Nobel Prize for carbon nanotubes, because there's the buckyball. What is the buckyball? What is a buckyball? It's carbon. Yeah?
Nets of graphene which is stick together and makes a ball.
Yeah. C60, right? So it's a ball out of graphene, out of carbon. So the buckyball got a Nobel Prize. So the ball out of graphene got a Nobel Prize. The flat sheet got a Nobel Prize. The only thing which is in between the ball and the flat sheet is the cylinder, the carbon nanotube, and it doesn't got a Nobel Prize till yet, but it's quite expected because graphene, so the piece, the sheet has it, the ball has it, so the cylinder should also get a Nobel Prize, right? But you see that Andreas Geim is also in the Guinness World Records. And he is in the Guinness World Records because he's the only person who won a Nobel Prize and won another prize. Do you know the other prize? Which could it be? The only person who won both. What kind of prizes do you know in science? Do you know any prizes, famous prizes related to the Nobel Prize?
IG Nobel.
Yeah, right. What is this? IG Nobel. Exactly, that's the IG Nobel Prize. So the IG Nobel Prize, I have it here. Honor achievement that first make people laugh and then make them think. And that's kind of like a funny Nobel Prize, but it has to be real research. So for example, research that shows that pizza is healthy. Pizza is healthy, basically, compared to different kind of how do you eat. Pizza could be healthy. Or that they see that if you go in cinema, the air smells differently if you watch a horror movie or not, due to the sweat the people digest and the consistent of the sweat. This kind of research is awarded by the Nobel Prize. And Andreas Geim, by the Ig Nobel Prize. And Andreas Geim also got the Ig Nobel Prize for levitating frogs. So basically, he showed that in a strong magnetic field, you can levitate frogs, which is really funny because you see frogs flying around. and he wants to prove that you can levitate things. And basically, why does anybody know why he looks at frogs? Levitating is a magnet field. Why could a frog be interesting? Yeah?
Because of the shape of its legs, some nano shapes are.
No. The frog is flying around in the air. He's levitating, like magic. But why a frog? Yeah?
High concentration of polar particles in his body.
Yeah, what is a lot? Not ions, but the frog consists a lot of, much more than we. Polar, what is a polar molecule? Yeah, but the one you know, most easiest polar molecule. Water, exactly. So the frog has a very high water content. And the magnetic field interacts with polar molecules, as you said, so with water. And this is why he showed with frogs that you can levitate them. So they fly around. And for this, he got the Ig Nobel Prize. The next Ig Nobel Prize will be 12th September. There's always a live stream from MIT, and they will award the next Ig Nobel Prize. There's also a very cool one for Professor Fish, and Professor Fish is doing research on fish. So he also won a Nobel Prize, and he figured out how airplane wings should be better to save money. To save fuel. Good. So he's the only living person who won both prizes, and this says a lot about his research and how he's doing research. And this is something I really like. Always consider how people, the character of people when they do research. And he did also something related to the lecture today, and this is what you see here. But next to winning a Nobel and the Ig Nobel Prize, he developed the Gecko tape. And Gecko tape is a tape you see here, and to prove it, he took his tape and put it on the top of a Spider-Man figure. And the Gecko tape is an adhesive tape which works like gecko sticks. And this is something we will figure out in the lecture. We will figure out how a gecko sticks to ceilings and walls. And Andreas Geim made a product out of it. You can buy it nowadays, and he uses the principle the gecko uses. Another thing where adhesion is extremely important is fluidization of nanopowders. We will talk about this also in the other lectures, but as you see here, so this is 10 nanometer titania, which is fluidized in a fluidized bed. So there's an airstream coming from below to fluidize the particles. But if you look at the scale bar, this is not 10 nanometer, it's 4 millimeter. Why the particles are 4 millimeter? This is 10 nanometer, titania dioxide, but we see 4 millimeter. Why? Yeah? Yeah, which stability? Yeah, they are not stable. That's a good point. But the question I have is, so that the material I fluidize here is 10 nanometer titania. But if you take a look, these white balls, this is the 10 nanometer titania. But the scale bar is millimeter. So why they are not 10 nanometer?
They adhere together and make microparticles.
Exactly. So the small nanoparticles, basically, they cannot be really fluidized. They are too sticky. The adhesion is too strong. And they form what you see here, these kind of agglomerates. And these agglomerates consist of even smaller aggregates and agglomerates. And due to the adhesion, the strong adhesion between the nanostructure, they form agglomerates. And these agglomerates are hundreds of microns or millimeter. And these can be fluidized, not the individual nanoparticle. So here, the adhesion basically is the driving force of building up these blocks. And another thing is, we talked about gas sensors quite fast, but if we make these gas sensors with flame processes, one very important question is the stability of the sensor. So the sensor needs a high porosity to get a very, very high surface area, but the higher the porosity, the lower the stability. Also, when it comes to self-cleaning surfaces basically work like the Gecko food. It's basically the same, but the application is different. And there you make a nanostructured pattern, but this has to be stable. And this is a very big problem with self-cleaning surfaces. And one very cheap trick is to sinter the particles, but we not always want to do it because this loses surface area. And this is, for example, something I investigated with a master student 10 years ago, and there we used mechanical compression. And the compression kind of decreases a little bit the porosity, but strengthens extremely the adhesion between the particles, and with this, the stability of the sensor. And also here, for my favorite example, of course, the question here is, do we have pure nanoparticles? No, also the smoke particles agglomerate. And when we talked about filters, right, the question is, how do the particles stick to the filter fiber? In the past, we just said, okay, they stick, they hit the wall and they are gone. But basically, adhesion tells us how they stick to the fiber, how strong, and how this works. Good. I don't want to have the animation. The importance of adhesion, this is basically the calculation from a very old paper, but I really like it. So this is basically the square cube law. What is the meaning of the square cube law? We already had it quite in the beginning of the lecture, first lecture, square cube law, strongly related to nanotechnology. Mm-hmm. Yeah, exactly. So the relation of surface area to volume. And basically this is translated into forces now, because gravity is what kind of force? Gravity is a?
External.
And that's Navier-Stokes equation. That's something completely different. We talk here about surface to volume ratio. Gravity is a? Surface or body? Volume, exactly. So gravity is a body force. Gravity depends on the volume, on the mass of a body. And this is how gravity goes for two spherical particles. So if you have two moons or whatever, then you can make the calculation. And this is the size of the particle, and we are here in microns. And then you see that gravity is far below capillary van der Waals electrostatic forces. But if we go into millimeter, centimeter, meter, gravity will very strongly overtake the others, and the others will not be important. As for us, adhesion, van der Waals, electrostatic is not really important because we are much bigger than microns. But now we see here capillary, van der Waals, electrostatic. So what kind of forces are these forces? Gravity is a volume force, and these are exactly surface forces. They act on the surface. For van der Waals, we could discuss a little bit more, but basically we consider them as surface forces. And this means for very small structures, they are much stronger than gravity. And this means if we look at small nanostructures, and then we go very to the left, right, because it's micrometer, for small nanostructures, adhesion forces is the same as for us is gravity. And always when you read or see any science fiction, you always can make the proof, do they consider adhesion in the right way? Because adhesion is a crucial problem when you are on the nanoscale. For example, when we talked about the cleaning of the wafer, right? We want to prevent dust to go to the electronic wafer, to the circuits. Why? Because the adhesion is so strong that it's not easy to remove them. You want them not to go there. For a centimeter, it doesn't weigh. You blow them away and then they are gone because the adhesion is not very strong. Good. So now I would like to make a very crucial distinction we need here for our iron-iron. And this is the distinction between a chemical force and a physical force. Do you know anything which we could put here or here? Do you know anything about a chemical force, an example for a chemical force? Do you know anything characterizing a physical force, an example for a physical force? Any ideas? Yeah? Yeah, perfect. So a covalent bond is a chemical force. A covalent bond would be in graphene, in carbon nanotubes, and so on. This is how the atoms are bonded there, covalent bond. Anything else? Yeah? Van der Waals for chemical or physical? Chemical. Okay. Anybody agrees or disagrees? Disagree? Why?
Because there is no connection between the atoms in van der Waals force. It's physical. It's just a stick to particles of molecules together, not in chemical. There is no chemical bond.
What is the difference between a physical and a chemical bond?
Material is changed.
The nature of the mixed material is changed. Okay, very good. You also showed up, right? No? Okay. What else? What is the difference between a chemical and a physical force? Yeah? Okay, so in a physical bond is just attraction, while in a chemical bond they are connected. How are they connected? What is the point which connects them?
Like for chemical, it's like atom and molecule interaction. For physical, it's like object and particles.
So physical is objects and particles, and chemical is atoms and molecules.
Just like the difference between a chemical and physical. Physical is maybe physical is always most of the time reversible, but chemical is may or may not be reversible.
Okay, so physical is reversible and chemical is not or maybe not reversible. This is basically something you see in a phase change. Because when you go from a liquid to a solid material and you have a physical bond, you just can liquefy the material. In a chemical bond, you destroy the material. So salts, for example, are physically bond, even as a solid. But you easily can liquefy them because you don't destroy the bond in this case when you change the phase. But we are still not completely, yeah? Charges play a role by chemical forces. Okay. What else? Yeah?
I think ion bonds and gravity for physical. Ion bonds is chemical and gravity is physical.
Ion bond is chemical. Gravity we don't consider here. Adhesion can be chemical or physical. Good. We collected a few things. Some of the things you said were correct. Some of the things were correct. I don't put it on a board because we have them on the slide. Some of the things were not correct. And basically the distinguish we make here is so a chemical force is, as you said, a covalent bond or covalent forces. And the point of a chemical force, and this is what you tried to describe a little bit with somehow different, somehow the same, is that electrons will be shared. So two atoms share their electrons. That's a chemical bond. And this means these two atoms lose their discrete nature. They are not two atoms anymore because they share their electrons. And from there you get a molecule. And this happens in fixed angles. Okay, these are all these orbitals, everything you learn in chemistry, right? These directions, angles, and so on. And in a physical force, the force is not directed. And atoms and molecules can move, but they stay connected. In a chemical bond, they are fixed due to the fixed angles. In a physical force, they can move around, and this is why it's very good for liquids, because there the molecules move around. So in a liquid, the molecules are bonded based on a physical force. And the difference is that in a physical force, the electron cloud is just shifted. So this means that, of course, charges can play a role, but basically, these two things go here. Okay, an ion bond is nothing else, we will see this in a minute, than electrostatic interactions. And these electrostatic interactions are always physical forces. And the nice thing is that for adhesion, what do you think is for adhesion important? Chemical or physical forces? Yeah? Physical? Yeah. So basically it's both, but chemical forces we don't consider here in this model. Chemical force means the particles have covalent bonds, so they sinter. So you really melt them together. But in adhesion, and this is somehow adhesion, but what we consider here in adhesion is the physical interaction of particles. And this is here. All the models I will explain you are based on physical interaction of particles. And this is very simple, basically, because it just starts with this law, Coulomb's force law, because Coulomb's force law describes electrostatic interactions. So we have an ion or a charge, and the charge creates an electric field. So the electric field E has, and any distance from the charge, we can describe the electric field or the strength of the electric field. And this is as the strength of the electric field depends on the charge. The stronger the charge, the stronger the electric field. 4 pi. What is epsilon 0? Yeah, permittivity. Permittivity, basically, we had this also in scattering. Permittivity tells you how easy you can move the electric charge in an atom or in a molecule. When you can move them very, very easy, the electric permittivity is high. When you can move them not so easy, because you have, for example, a high electronegativity, fluor really takes electrons, then it's not so easy to move them around. So why there is an epsilon 0 and an epsilon? Yeah? Yeah. So 0, 1 is in the vacuum. And the other epsilon is for the medium. So when we are in air, for example, or in water or whatever. So now we just have to, this is only one charge, but if we want to have, this is the strength of the electric field, and if we want to go to a force, we need a second charge. I don't have the units here, but then you get the Coulomb force, and this is the electrostatic force between two charges here. Ion, ion. Okay, so this is the adhesion basically between two charges, two ions, or whatever. So to describe this case, we just need Coulomb. That's it. And then we have all this. And with this, we have this one. So extremely simple. One thing I want to mention is that when we talk about particles, we very often use forces, adhesion force. But when we talk about molecules in the books, you don't really use force, you use another term. Do you know the other term, which is often used for ions, for atoms, molecules? It's not adhesion force, it's... Yeah? No, cohesion is something else. Cohesion is basically adhesion in the same material. Strongly or very correctly, adhesion refers to different materials. Cohesion is within one material.
Van der Waals forces?
No, Van der Waals forces is something different. We will talk about this in a minute. Yeah? Yeah, interaction energy. So when we look at molecules, we very often, or the books use interaction energy, and particles, you talk about adhesion force. What is the relation of energy and force? Mathematically? Or is there no relation? Yeah? Times distance, yeah. Here. So the force is the integral, no, the interaction energy is the integral of the force, or the force is the derivative of the energy to distance. And if you look at the units, Newton and Joule, you will see the one has m, so kilogram meter divided by second square, and the other one is kilogram meter square divided by second square, so one derivative respect to the distance. So you can use it vice versa. I normally use adhesion force because I work with particles, but the books for molecules always use interaction energies. And if you make a very easy calculation for two ions, so and you say, okay, I want to calculate their interaction energy, and I want to compare it to their thermal energy. So interaction energy makes them stick together, and thermal energy makes them, yeah, not repel, but not separate, but
Kind of unstable.
yeah, unstable. They move around somehow, right? It's not that the thermal energy pushes them away, but the thermal energy gives them random movement, and the adhesion gives them sticking together. So the question is, which is stronger? And if you make the calculations for two ions based on Coulombs force, the interaction energy is 200 times stronger than the thermal energy, and this means that a physical force can be exactly as strong as a chemical force, because this is exactly the 200 times kT, and this is what we have in salts. Okay, so if we have ions sticking together, they are very strongly sticking together. And now we can just make it a little bit more complicated, because now I want to go from ion to ion, Coulombs force law, to ion molecule. What is different now? The only thing which is different is that a molecule has a dipole moment. And also in light scattering, we talked about dipole moments because the wave goes up and down and it creates dipole moments in the molecule. And this gives these kind of different radiation. And a dipole moment means that you have charges which are somehow separated in your molecule. So it's not perfectly everywhere the same or a homogeneous distribution of charges. And these charges within the molecules have a certain strength and a certain distance. And so here's plus Q, minus Q, and this is the distance L. And this means the dipole moment is the charge times the distance. And here is a very prominent molecule, HCl. So the chlor takes all the electrons. It attracts the electrons stronger than the hydrogen. And this means this molecule has a permanent dipole. And the dipole is mainly shown as an arrow. And the arrow goes from minus to plus. So we have a direction of it. And there could be an induced dipole. So it means you have a neutral molecule, but in the molecule you induce a dipole as here. So you have glycine and you put it in water, and in this way you induce a dipole. You also can induce a dipole if you take a neutral molecule and you put it in an electric field. And if you put it in an electric field, the electrons will arrange to the electric field lines, and then you create a dipole in your molecule. And the third one is the fluctuating dipole. And the fluctuating dipole means, what means the fluctuating dipole? It's a good question. What means fluctuating dipole? Yeah?
It's changing its polarities according to.
Yeah. 10 to the power 14 is hertz, so very, very fast. And it means the electrons move around. And they are not always homogeneously separated. So for each thousandthstel or billionstel of a second, you have a small dipole in your molecule. And this is changing all the time. So these three kinds of dipoles we have, we ignore them for a while. But what we do is we replace one ion and put a molecule here. So we have water and Na+, for example. Now we have the interaction between ion and molecule. The interaction is still the same, Coulomb force law. The only thing we have to do is some triangular math. Because now we have a charge which is positively here in this case, and then we have a positive charge here and a negative charge here in the dipole. So there will be an attractive interaction from here to here, plus and minus is attractive, right? And there will be a repulsive from here to here. And now we can calculate the interaction energy the same as we have it here. Okay, this is basically Coulomb's force law here. We take the same law, the only thing we have to change is that we don't have charge 1 and charge 2, but we have charge 1 and we have the dipole moment, the strength of the dipole moment. So this is the small q. And the distance now changes also, because the distance is from A to B and it's from A to C. And this means that the interaction depends on the orientation, so how the arrow turns. So if minus Q is very close to Q, we will have attraction. If minus Q is far away and plus Q is very close, we will have what? Yeah, we use another term for it. It's correct what you say, but we use another term for it. We will have repulsion. Repulsion. Good. So this is what you see in the equation. So here is the angle. Here is Q and the dipole moment. It could be small q or mu, right? Yeah, mu. And here everything else is the same. The only thing which changes is that for ion, the interaction energy depends on the distance 1 to the power x. And now we make one of the ions, we make a molecule out of it, and now it's more sensitive to the distance, 1 divided by x squared. So with changing these things, the physics is the same, it's electrostatic. But due to the geometry, it gets more sensitive to the distance. And this means if we would make the same calculation we did for two ions, we would not have 200 times kT, but if we have Na+ and a water molecule, we would have 34 times kT. So still strong. And this is the reason why after thunderbolts you get raindrops, because you have ionized, you have ions in the air, and the water sticks 30 times stronger to the ion than just going around. But it's already a factor of 10 weaker than here. Okay, so the interaction energy from here to here is 10 times weaker just because of the geometry. So means we just make Coulomb's force law and we can describe the same. And now we make dipole-dipole interaction, so now we make two molecules out of it, and it's still Coulomb's force, it's still electrostatic interaction. And you see the interaction energy goes now 1 divided x to the power 3, so it's even more sensitive to the distance. And we don't have a charge, we have a dipole moment, a strength, right? And we have the angle theta 2, the angle theta 1, but now we have a third angle. Why we have a third angle now? What changes now that we have a third angle? So if we have one ion and one error, yeah?
There should be a rotation of molecules
Yeah.
to a space angle.
Exactly. So if I have this case, it doesn't matter if one error is like this or like I can picture all angles by just one angle. But if I have two, it doesn't work anymore because they could be like this or like this, like this, like this. So I need a third angle to describe the positions. The easiest way is maximal attraction, and maximal attraction means all angles are 0, and then the equation is very simple, and it comes still from Coulombs' force law. The only thing which changes is we need the strength of the dipoles instead of the charge, and now the dependency on the distance is 1 divided x to the power 3. So, if we now would do the calculation, interaction energy to thermal energy for two water molecules stick 3 times stronger than kT. So this decreases more and more and more. So now we are in a region where thermal energy and interaction energy are quite close to each other. And if you think about the melting temperature and what's it called? So the phase transition from ice to water and water to vapor, then we are in ambient conditions, right? 0, 100, so 3 times kT. And we could also include this kT in this equation because I not always want to calculate Coulombs' force and the kinetic energy and compare them. I would like to have one equation which directly considers the thermal energy. And if you do it, it goes a little bit more complicated. This is the way how it's done. In general, the angle averaged free energy of an instantaneous orientation-dependent free energy is given by the potential distribution theorem. And then you just do this. But at the end, you will come up with this equation. And this equation, U, in this case, I just copied it from the book. U is mu. So you make out of mu1 and mu2, you make mu square. This one you should recognize from here. And kT is the thermal energy. But one thing extremely changes. What changes extremely from the left to the right equation? Yeah, and where do you see the distance now? Yeah, to the power 6. So in the book they use r. I make everything to x now because r for me is something like a radius or so. But here in the book they use r as a distance. And now from to the power 3 you go to the power 6. So it means for two molecules interacting with each other due to physical interaction, which is basically electrostatic, which is basically Coulombs' force, and you consider the thermal energy, the interaction energy depends 1 divided to the power x, 1 divided x to the power 6. So it's extremely sensitive to the distance. Do you know how we call these force here? All of you know. What is this equation? Make a guess. Adhesion is, as I said, an umbrella word. It has no meaning in this way. There's no equation for it. There is an equation, but what kind of adhesion? This is a very specific. This is one of the first term I want to add here, basically. What is this? Yeah? Yeah?
Maybe because like there is a term R at the
No, no, it's a good idea, but for newtons, it's not to the power 6.
Like there are two bodies and with the R there.
Yeah, that's correct, but there is not to the power 6. It's a good idea, but it's something all of you know. So what is it? Van der Waals force. This is Van der Waals force. Okay. So Van der Waals force is the electrostatic interaction between molecules considering their thermal energy. This is Van der Waals force. And this is why Van der Waals force is an adhesion force, why it's an electric force, and so on. And Van der Waals force has 3 different types. So Van der Waals can be even grouped into Coulomb, Dubai, and London. Does anybody know where these 3 are coming from or referring to? We already had it on the slides. Yeah. The type of, what kind of interaction? I think it's the type of? Yeah, very good. The type of dipole. We had 3 kinds of dipoles, and the dipoles here is just a number, but it could be a different kind of dipole. And this means that we can have Coulomb interaction, and Coulomb interaction means we have 2 fixed dipoles. That's it. Very strong molecules, or molecules with a very strong dipole. And then it could be that we have one molecule having a dipole, and this dipole generates an electric field, and this induces in a second one a dipole. This is Debye interaction. And the third one is the fluctuation, right? So it's already, all the time it's moving, and all the time it's generating electric fields. And then when a molecule is very close to it, then they kind of interact with each other, and they will keep the electrons in certain positions. So interactive, how to say, interactive, I'm missing the word, situations are more likely. And in the literature, so the question now is, which is the strongest? All 3 are the same, 1/3, 1/3, 1/3, or is one of the 3 stronger than the other one? What do you think? Yeah? Dipole is the strongest. What else? Any idea? Yeah?
I would say maybe London.
London, okay. What else? Do you remember why London?
Because of the fluctuating dipole, and I think the high frequency.
But does this makes the strongest? I mean, that's the explanation how it works. I will show you the data. The data is here. So we have orient, induced, disperse. You will find the names vice versa. So this is Coulomb, Debye, and London. And the C basically is, the C refers to so all the physics is here, right? So the C is kind of a simple variable to explain dipole moments, permittivity, and all these things, they go into C. The only thing you put out is the distance, because this is the variable where you normally make the calculation on. So then we have a C for Coulomb, we have a C for Debye, and we have a C for London. So which one is the strongest now? If you look, for example, for CO2 or for HBr or for CH4, which one of them is strongest? Which one is the strongest? Huh? London, exactly. So if you look here, this is London, and it's always much, much stronger than the other ones. There's just one expectation. Expectation? No. One. Huh? Exception, thank you. One exception. Which one? Water, right? And that's so cool. So anomaly of water, hydrogen bonds. So basically for water, the orientation, which is this one, is much stronger than the other because it's a very small molecule, but a very polar molecule. And this means for water, Hysum is the strongest, while for the other one, London is the strongest. And since London is the strongest, you very often find in the books this explanation for van der Waals forces. But I want you to understand that van der Waals forces is one part of adhesion, and van der Waals forces depends on 3 different types of dipoles. And this is Hysum, Debye, and London. And this means you have a fixed dipole, this means you have an induced dipole, and this means you have a fluctuating dipole. And generally, the fluctuating one is the strongest, but all 3 together are van der Waals forces. So if we take a look, we would make F adhesion, we would have now van der Waals force, okay? But there is still stuff missing. Any questions to this? Good, because we have to hurry a little bit. We didn't make the last one. And the last one is quite simple, because for the last one, there is a paper from a guy called Hamaker. That's the paper here. And what he did is he took the London van der Waals, but it counts the same. He just made the calculation on the London one. But what he did is he said, now basically, if I have a particle here and here, particles consider out of molecules, right? So basically I have a lot of dipoles here. And I have a lot of dipoles here. And thanks to this, I know how to calculate the interaction between 2 dipoles, right? I know this. So I just can sum it up. I just can make an integration over the full particle. So it means I assume that the interaction from here to here is not disturbed by the other ones. It's a very strong assumption, but it's an assumption. And then I just have to calculate the interaction from here to here, from here to here, from here to here, and so on. And then I do the same with this one, here. So basically, I just have to sum up everything. And when you sum up everything and solve the equation, he did it for 2 geometries. One is 1 particle and a plane, so like a ceiling. And the other one is 2 particles, which are spherical particles. You end up with these equations, and these equations are extremely simple. Because the only thing you need is AH, this is the distance, and here is the radius of the 2 spheres, and here it's just 1 sphere, so just 1 radius. What is AH? Yeah? Yeah. Do you know the name of it? This is the Hamaker constant. And the Hamaker constant contains all the physics. Because R is a size and X is a distance. So all the physics is in the Hamaker constant. So it means that everything we have here in these C, or we have here in, right? So these mu square, epsilon 0, epsilon, kt, all this is in the Hamaker constant. And once you know the Hamaker constant and you know the size of your particle, it's extremely simple to calculate the van der Waals force. Over distance, or you set the distance. Distance is set very often as 0.3 nanometer. So what we need to figure out is to calculate van der Waals forces between spherical particles. We need to know the Hamaker constants. There are two ways to get it, by experiment and to calculate. And by experiment, we will talk in 2 weeks. When we talk about experimental methods, then I will show you how to measure Hamaker constants. But to calculate is also quite simple, and there's a reason why I choose these two images. Who knows these series? Yeah, Simpsons and? What's the other one? Yeah? Okay, Futurama. So in my generation, we know all of the episodes by heart. I think in your generation it changed a little bit, but the offers, we don't have Netflix on these things. So Simpsons Futurama was running at 7 o'clock in the TV, so everybody was watching Simpsons and Futurama. But the cool thing, and this is like a small side story about this, is that what do you see on the board here? Equations. Random equations. If not random, but what kind of equations? So the episode where you see the right one is called The Prison of Bender. And in the episode The Prison of Bender, Amy, which is a young girl, an intern in the company, is annoyed of her young body because she always has to be thin. And she wants to go into an old body to eat as much as she can. And Professor Farnsworth, who's an old guy, wants to become young because he's annoyed of his old body. And he developed a mind-swapping machine. So Amy and Professor Farnsworth swap minds. So Amy goes into the body of Professor Farnsworth, Farnsworth goes into the body of Amy. But very fast, they figure out they don't like it and they want to go back. But the machine doesn't allow this. You cannot swap minds twice. And then Bender comes as a third one and he says, I'm a volunteer, so over my body you can go to your old bodies. But if you make the math, you figure out it will not work. So they looked for a fourth one, a fifth one, a sixth one, a seventh one, and so on. And you have to know that the producer of this episode has a PhD in math from Harvard. And this is the nice thing of this thing. So he has a PhD in math from Harvard, but he doesn't work as a mathematician. But it means if you have an engineering or math degree, you can do very cool things in your life. So he basically writes episodes for Futurama, for The Simpsons, and so on. But sometimes he gets bored and he solved these mind-swapping problem. This is a known problem in math. It's basically about logistics and here it's called optimization problem. And it's called nowadays Futurama theorem because he solved it, but then he decided he will not publish a paper about it. He said it's not important enough, but he made this episode about it to state the problem and secretly show the solution. And the solution is you need 2 additional people. With 2 additional people, it doesn't matter how many people already switched minds and bodies. With just 2 who don't participate, everybody can go. So this is the most efficient way, 2 additional people. Good. The equation here is not this equation. The equation here is from a Russian guy called Lifshitz. And this is an equation to calculate Hamaker constants. The equation looks complicated, but it's not. Actually, the equation is very simple because what do we need? We need 3 divided by 4. We have it. Kt, basically very simple. H is a constant. And then we just have a lot of epsilons. And epsilon is permittivity. And permittivity is a macroscopic measurable property. And a macroscopic measurable property is the best you want to have because it's very easy to measure. So it's a macroscopic body and it has a certain property and it's nothing like these molecular, atomic, whatever. So it's very easy to get. But we have different ones. We have permittivity here and we have here a permittivity and this permittivity depends on the frequency. And now the question is, we already had today a frequency dependency. Where? Where did we had already a dependency from the frequency today? Yeah? Where we had today already a dependency on the frequency. We already mentioned this. This is frequency dependent. Yeah? We didn't have it today, the Maxwell equation. It's correct, but we had today the frequency dependency. Yeah, exactly. So this one depends on frequency, right? So now you see the right part depends on frequency, the left one not. And basically the equation is the explanation why London is always stronger than the other two. The other two are in the left part of the equation, and they cannot be larger than 3 divided by 4 kT. That's the maximum. But the right part then gets much larger. And the right part is London interaction. So this is basically the explanation why the London interaction is so strong. Epsilon 1, 2, and 3 is you have material 1, material 2 interacting through material 3. Good. Now I would like to go into an example. I need 20 minutes more because the repetition at the beginning took so much time. But I want to finish this topic today. So I would like to take a look at this one. We already mentioned it. So the question is, why sticks a gecko to walls? So we have a Tokai gecko, and he has a weight of 50 to 100 grams, and he can carry up to 40 kilograms. So two of them could lift a normal adult, right? And then you see on the feet are hierarchical structures. How does a gecko adhere to a surface? How works the adhesion of the gecko? Yeah?
Their feet have some nanostructure.
Mm-hmm.
Has some nanostructure. So because of the existence of these nanostructures, there should be van der Waals
Mm-hmm.
force between its legs and the surface. It is sticking.
Mm-hmm.
So because the number of these nanostructures are really high,
Mm-hmm.
so the van der Waals forces is also really high, so it can hold, for example, 40 kilograms.
Exactly. So the important thing is that the gecko has a Hamaker constant to a roof, a window, or whatever. And my hand has a Hamaker. Here is van der Waals interaction between my hand and the table. I don't feel it, the gecko feels it. Why? The Hamaker constant is the same. The physics is the same. There's no difference to this. But if you put the table under the microscope, it will have a surface like this. If you put my hand under the microscope, it will have a surface like this. And this means that my hand and the table only very seldom come close enough to make these attractive 1 divided x to the power 6, right? A little bit away, no adhesion force or no van der Waals force. While the gecko has all these tiny hairs, and the tiny hairs take care that he always has no distance. And when he has no distance, he's extremely strong connected due to van der Waals forces. So physically, from what happens, there is no difference between my hand and the gecko. But what is the difference are these hairs who can make use of the acting force because the distance is reduced. And this is what you see here. So here's the foot, here's the toe, here's the lamella. This is the first structure. Then you have hairs, and the hairs are like a very hierarchical structure which have even smaller hairs, which are in the range of 100, 200, 300 nanometer. And this is quite cool because we see again the square cube law, because the bigger the animal, the more complicated the hair structure on the foot. So an insect, which is much smaller, has also tiny hairs, but not this hierarchical complicated structure. But the gecko is very big, and volume goes to the power 3, right? So the structure, he needs to get more contact to the surface than a spider or a fly. And this is why he has 2 levels of hairs, which are micro and nano size. And there's also another thing, this is what you see here. The foot of the gecko, he goes like this, and like this. And this is, he cannot go like this. And the second one is, he sticks so strong, he cannot lift his foot. What is he doing? You can see it on where the laser pointer is. What can he doing? So he sticks so strong to the table, he would not be able to go away. How can he get free?
By using
Yeah, but how? Yeah? No, not in cross lines, Yeah, he rotates, but how he gets free? Yeah, he rotates, I think it's correct. What he has to do it slowly, like this, right? He cannot go like this. And to be able to do it, the gecko can move his toes upwards. Like we cannot, we are blocked here, right? But he has to get free. So the gecko can move his toe, not like the finger we have, but he can do it upwards to release them. And this is, if you look closely, you see it also in the image. So people were really interested in figure it out, and we don't know it so long. So there is the question, how do you measure it? And the first idea was just to measure it. So they took a hair and put it on any kind of sensor, and then they said, okay, we can measure this adhesion force. The number is not very good, but at least we were able to measure it. And then they want to figure out how the adhesion works. So it was about 2002. And this is how to measure. Take a gecko, take a glass, and just pull and push and pull and push. But this is not really scientific what you do here. But at the end, they figured out, okay, it has to do something with van der Waals adhesion. So here we are. And at the end, and this is what we will get to know in the experiment part, they take a hair and put it onto an AFM. And the AFM is a machine where you can measure forces. So you can measure adhesion forces. And now I would like you to make a small calculation, because we already got equations from Hamaker. And this is the equation we got in the paper, right? And in the paper, or this is the model, and if you look at one hair and the surface, we can simplify it and say, this is the surface, this is the gecko hair. So if you consider now, R is 100 nanometer. And X is 0.3 nanometer. That's a very common value if you want to see the distance between particles. And the Hamaker constant is, I think, 20? No, 6.8 to the power 20. 6.510 to the power 20. And then I give you the equation because the slide is not here with the equation. So this is the equation. Hamaker constant times radius divided by 6 square. And now I would like from you the number to calculate. Oh, I want to take the camera at least to the... And at least we have the equation. Okay, should work. Anybody has a number? Yeah?
1.2 minus 10 to the power of minus 7.
Minus 7.
Not minus 7. 10 to the power of 7.
Minus 8. Yeah.
Minus 8?
Let's see. So 1.2, 10 to the power minus 8 Newton. This is 12. How could I also? 12 nanonewton. Okay. So now let's take a look, because they measured it, right? So if we take a look at the measurements, and this is the case we're looking at here, 12 nanonewton. So we are very, very close to this one. Okay? And this means theory describes very well experiment. We have a lot of assumptions here, and there's a lot of possibilities to attack this result and discuss this result, because basically it depends on the Hamaker constant, and the question is, what is really in the Hamaker constant? This is a research question, basically, we do. But in a very simple and first assumption, adhesion for a Gecko is well described by the very simple model from Hamaker. Okay? With this, I would end the class for today. Unfortunately, we are not finished with the adhesion model, so we need some time in the next class. But I would like to stop with a last question here. And this is basically one of my favorite questions. So the Gecko sticks very, very strong to a ceiling. Sticks a Gecko to a Teflon pan? A Teflon pan is designed that nothing sticks to it, right? And a Gecko is designed to stick to something. So would a Gecko stick to a Teflon pan? Yeah? Okay. No? No? Why not? That's the most common answer. What is the surface in the Teflon pan? Actually, it's very rough. It's made out of pellets and pressed into it. The pan surface is not extremely smooth. But there's another explanation. Yeah, hydrophobic. And this hydrophobicity has to do with this one and this one. So who thinks the Gecko will stick? Raise your arm. 2, 3, 4, 5. Who thinks the Gecko will not stick? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. He does not stick. But you even can explain it. What is one main ingredient in Teflon? Element. Fluor. And what do you know about fluor? Exactly. Fluor has the highest electronegativity. What is the meaning of electronegativity? Yeah?
The dipole moment is really high.
Yeah, what does the fluor not allow? Yeah, why not? What does electronegativity means? What does fluor is doing?
It takes
Yeah?
the electron.
It takes the electrons and it doesn't give it away. So the gecko cannot induce dipoles. He cannot move the electrons around. So he cannot activate this one. It's not this part, okay? And this is important to read. I mean, it's a funny example and so on, but you really can explain all the concepts on this example. He cannot move the electrons because of the high electronegativity. So no London force. London is the strongest of this one. So the others are very, very weak. So no van der Waals forces. So no adhesion forces. So the gecko doesn't stick. Okay? Good. This is a good point to finish the class for today. Sorry that I took a little bit extra time. And we will still need till next week because we are missing something. And this is not the full story. And this is what we will make next week. So this means we have half an hour break now. Then I will see you in the seminar. And next week we will finish this question. So thanks a lot and see you in half an hour.